Hey everyone, I am here today with Gene Watson, HRP's Regional Manager in the St. Louis, Missouri office, as well as our lead in the Midwestern region. And Gene's here today to talk to us about one of the projects that goes on in Missouri. Now, some of the biggest and most important projects in the company's history have been handled through the St. Louis office. And Gene is here to tell us about one of those that we have pretty interesting drone footage of. So Gene, can you tell us a little bit more about what this project was and the tasks that we're going to see today?
Yeah, thank you very much, Tom, for the nice introduction. This site is the Carburetor Superfund site. It's a 20-acre facility that we completed in May of 2020. We started the entire Superfund process, believe it or not, in 2005. And that involved two big phases where we did an engineering estimate and cost analysis, and then the second phase, which started roughly in 2014, which was remediation of the site. The site goes all the way back to the early 1900s, and over time the facility grew to where in its final configuration it occupied about 450,000 square feet on that facility. This project had basically four main phases to it. This footage we're going to talk about today, the former TCE AST area, they had a 12,000 gallon AST. Back then it wasn't, back in the 50s and 60s, it wasn't monitored. We don't have the same environmental laws that we have today. It slowly leaked over time, roughly putting a little over 40,000 pounds of TCE into the soil and groundwater. Main contaminants in the site that drove this cleanup were PCBs, and the PCBs came in the form of hydrol oil, which was actually produced in St. Louis by Monsanto Corporation. It's a hydraulic fluid. The PCBs really made this hydraulic fluid stand up well to heat and the pressure that's required for those die-cast machines. Unfortunately, it led to gross contamination at the site. We had in some places up to 30% PCBs in the soil. Then that was in the die-cast area mainly. And then there was also asbestos, lead because of the age of the building, of course. We had metals, we had USTs at the site that we had to close. Across the street there was a lab, and this lab had 8 USTs underneath it where they would test various blends of gasolines, diesels, things like that to the carburetors. And so those had to be remediated and closed in place. And then, that TCE area, we had to look at options of what we were going to do. We ended up doing an In-Situ Thermal Desorption by electrical resistant heating, ERH.
So you've just described the technical process of what the work was. Can you tell us a little bit more about what that actually means? What's actually happening here in the ground that's remediating the site?
So this ERH, ISTD ERH that it's called, is a form of in situ, meaning in the ground, whereas if you would dig it out, that would be ex situ. So it's a form of in situ remediation to where we apply heat to the soil all the way down. In this case, it was all the way down to bedrock, about 30 to 32 feet. By applying that heat, what that does is it thermally breaks the contaminants concerned down, which in this case was trichloroethylene, TCE, and its breakdown daughter products, 1,2-DCE, 1,1-DCE, and vinyl chloride, which are generated through natural attenuation. And then we collect those vapors in that network of pipes that you see on the video. Then they go through a series of various pieces of equipment over there, which include granulated activated carbon. We have some blowdown units, and then ultimately it goes through a thermal oxidizer to make sure that we're not releasing anything to the environment and to the neighborhood.
What apparatus here is actually sending that heat down into the ground?
Over on the upper right-hand side of the screen, you see a big transformer unit.
Yep. And
that's a 6 step-down transformer where we were getting the power from the direct local utility line out in the street. The line came underground, brought it up to the pole, we put it in there. It was a tremendous amount of power. So that had to be stepped down to where we could distribute it throughout the ISTD area. And the ISTD area was broken down into 3 areas. TZA, Treatment Zone A, which looks like a dog's head. TCB, which is on North Spring Street there, that little small rectangle, and then the remainder of it was treatment zone C, TZC, and that was where the TCE AST was located.
So looking at the footage here, we see the pipes and the lines running out to those areas. What are these kind of cube-shaped boxes where the lines seem to either feed from or feed out to?
So those 6 boxes that you see that are feeding those lines out, Tom, those are actually power control units. So that is where we took the power from that step-down transformer. It was distributed out to those. And then all those black lines that you see going out to TZ A, B, and C are actually copper wire that's approximately 1 inch in diameter that feeds this. As you'll note, you'll see a few other items in here as you're looking at it. There were 2 3,000 pound, what we call granular activated carbon vessels. What happened was as the vapor was collected in TZ A, B, and C, it would come back through these gray pipes that you can see in the picture, and it would go through the cooling towers, which are the large green structures, dark green structures right there, those two, and then they would feed into the 2 3,000 pound GAC units, which are just right adjacent to it. After they left there, then they would feed into the thermal oxidizer. In theory, after the thermal desorption was done, the ISTD, there was no compounds of interest left. Those bonds get broken and you end up with mostly water vapor and some various gases, none of which are really that harmful to the environment. We did all these precautions to make sure that we were not going to release anything. There you can see the Boys and Girls Club at the top of the scene. Another interesting thing to note is we also put water into the system. You got to have water there to make it work. And so when we heat up the ISTD system, we're heated up to a temperature of just right at 100 degrees centigrade, boiling of water. And the whole idea is that we want to drive all of the water out in the water, as in a water vapor form, collect that because of the TCE that's in the groundwater. TCE is a DNAPL, which is a dense non-aqueous phase liquid, meaning it settles on the bottom of the groundwater, and this is shallow groundwater, so we only had to go down about probably 12, 15 feet to find it in this case, as opposed to a LNAPL, which is a light aqueous phase liquid, think like oil, how it floats on top of the water.
Yeah.
Now, one other thing that's interesting to note when you look down on these treatment zone areas, each one of these little black lines sticking up where the cables go to, those are all thermal wells. So as you can see, we had a lot of thermal wells out there. We had well over 130 thermal wells across there, each of them going down to 30, 35 feet, stainless steel casings. And then the orange areas that you see on top of each treatment zone, that's actually a vapor barrier, pretty similar to what you would spray on as insulation in your home, believe it or not. You can see over here on the side of the left-hand side of the screen down towards the corner, that's a really good view of the thermal oxidizer. The contractor that put in the ISTD system was TRS, and they did a fabulous job of installing this and operating it with oversight by us. As you can see right now, there's some field workers out on site, and what they're doing are collecting samples with a Geoprobe to make sure that we're achieving our remediation goals at the site. Like I said, the primary contaminant was TCE. So as you can see, right there, basically in the center of the photo, Tom, is a Geoprobe out in the field with some HRP personnel collecting samples of the soil so we could evaluate how we were doing over time. You have to monitor that. You have to take samples. We took samples 2 times to see where we're at. We did some in the middle, and then we did it towards the end. And then at the end, we saw, hey, we're there. So then once we turned the system off, we had to go through and then do a final sampling to show that we had achieved our remediation goal of 24 milligrams per kilogram, or 24 parts per million for the TCE, which was a human health risk assessment number that we calculated during the ECA phase that I discussed earlier. It's important to note, though, we drove off concentrations of TCE well above 5,000 parts per million in several areas. And in doing so, we collected, destroyed approximately 40,000 pounds of TCE. Okay, the reason that we chose ISTD over a conventional ex-situ type of remediation of dig and haul is because TCE has a land ban number of 6 parts per million, meaning you can't dispose of TCE at a landfill above 6 parts per million when we perform this remediation. Those numbers may have changed, I don't know by now. The cost to do this by dig and haul and then take it to a waste facility that was approved by EPA and certified that could do incineration, because that was the only other option to get rid of this, would have been in excess of 10 to 30 times the cost of the ISTD work. So ISTD work is economical. Nothing leaves the site, so you don't have any legacies at a landfill that you got to worry about. And it's quick. Once the start to finish of this project took basically a year, was it.
How long do you think it would have taken with that digging things up and taking it to another site?
That's a great question, because in order to do this, we would have had to put a sprung structure around the facility because of the TCE vapors that would have been coming off. You got vapor intrusion problems because we had none. We sampled for vapor intrusion. There were no vapor intrusions in the Boys and Girls Club or the bank or any of the homes around there. So we knew we were okay there. However, to remediate this by digging it out and disposing of it incinerating it off site, you would have to put a sprung structure up over it in order to keep those vapors in there. You have to exchange the air 4 times an hour. It's a really entailed process. So we would have been there at least a year doing this. This is a really good shot of the 2 geoprobes out there that we had going, taking samples. We used a firm that we use all the time called BGS, Below Ground Surface. They do tremendous work. They worked at the Carter site with us during the entire time we were out there. Here you've got a great view looking down on the HRP personnel that are bagging samples, putting samples in jars, getting the coolers packed and getting everything ready to go to the laboratory. This process, when we would go out there and sample, would usually take us, probably about 3 or 4 days to collect all the samples we needed, get them packed up properly and off to the lab for analysis.
How many samples are we sending out per day or over time?
Well, with each event, we didn't, this isn't a huge sampling event. There were basically 2 big ones like this, and then a final one. You're looking at maybe, it's not a big one, we collected maybe 750 to 1,000 samples, whereas at the Carter site, when we were doing the site characterization and that, we had over 250,000 data points, and we had, 3,000 or 4,000 samples we collected.
So we're seeing, is this the samples here in the lower part of the frame?
Yes, that's correct.
Okay. And this to me looks like Decon possibly?
That's correct.
Okay. So this is kind of what the tools of the day, just being Decon in there?
Exactly. This is a classic setup for out in the field under HAZWOPER conditions.
And are these drums just for disposal of
PPE?
Yes.
Correct, and soil cuttings too that are not bagged. This is a great shot right here because you can really see the thermal wells. This is a really good view, Tom, right here of you're looking at treatment zone A that it's going to scan to, and you can see the thermal wells. Those are the black pipes sticking up, and as you can see, there's a cable, which is an insulated copper wire. The wire is, like I said, approximately 1 inch in diameter, and we had in excess of 1 mile of cable at this site, so it was worth a lot of money, as you can imagine.
Yes.
The gray pipes you see is the vapor collection system coming back from each of those wells.
That's that really thick gray line.
Correct.
Well, Gene, obviously a really impressive piece of work that HRP was able to do, and such a great thing that was able to happen for the community there. As we're closing here, what are some maybe final thoughts that you would like to leave the audience with about the site and the job? The
job was very successful. We cleaned up Superfund site in the middle of a residential community right next to the Boys and Girls Club. We worked over 2 million hours total at this job site over the 15 years without one single reportable, which we are very proud of. Safety was a huge concern, and we took it very seriously, and it showed without any reportable incidents. So we're quite proud of that. It was a huge team effort in order to get there, and we owe it to all of our subcontractors for their hard work in making sure that was done, achieving all of our remediation cleanup goals that was set by the Streamlined Risk Assessment that was done by Jay Peters with HLA, and most of all, we did not have one exceedance of any at the air monitoring stations throughout the entire remediation.
Well, everyone, thank you so much for joining us today. We really appreciate the opportunity to get to tell you about this amazing site that HRP got to work on and help out on, and the great work that was done by our St. Louis office out there. If you learned something today, hit that subscribe button, hit the like on the video, and the bell for notifications so that you see all of the amazing jobs and content that HRP is out there to provide. Gene?
Thanks, Tom.
Thanks so much for joining us today.
All right, have a good day.
Bye, everybody.
Bye.